So I'm just going to find out a little bit, how many of you are Java developers? Okay, what about C, C++ developers? The rest then. Or how many of you have written basic Android apps or Hello World type stuff? Okay, got it, cool. All right, so today we're going to talk about NDK, what it is, what it isn't, when you should use it, when you should care about it, that sort of thing. So that's basically what we are going to cover. Just before we get started, I'm just going to tell you a little bit about myself. So my name is Marco Garganta. My background is in Java. I actually stopped doing C when Java came out. It wasn't Java back then. It was a project at Sun called Oak. And I got really interested in that because we were going to program all the embedded devices with it. So that was kind of the selling point. So I kind of jumped on a whole Java bandwagon back in '96 and started developing in that. But as we know, Java sort of moved from the browser to the server side, and most of my development in Java has been with the big enterprise systems until Android came out. So that's why I kind of got back into Android when it came out, because that was my original interest in embedded devices. But I haven't done a lot of C, C++ development ever since the mid-90s. I used to do it before that. So that's a little bit about my background. So I've been doing extensively a lot of Android development the last couple of years. One of the first things I did is I developed a course for Americana called Android Bootcamp, which is about app development. And since then, I taught that course all over the planet. And then O'Reilly asked me to essentially bottle it into a book. So I wrote a book called Learning Android. That's been translated into many languages and so on. But that book is all about app development. Most of the stuff that I do nowadays has to do with Android internals. So basically not so much building apps, but building ROMs, like building actual custom Android devices. So that's kind of like what my passion is and what I do mainly. And so NDK nicely plays into that because NDK is sort of a nice little subset of actually working with the platform. I frequently speak at conferences. This is my third year at AnDevCon. I skipped 1 year, and this is my second talk today. So some of you might have been in my previous talk on architecting Android apps. So that's a little bit about myself. In this module, in this talk, what we're going to talk about is we're going to talk about basically what NDK is, why you would care about it. I'm going to mention JNI. But I'm going to refer you to another document that we wrote on JNI. I'm going to give you an example of how to use NDK. So basically, we're going to build an actual working example with NDK through the next hour, from scratch, from nothing. So that's basically what the talk is about. Now, just to kind of start nice and easy with some pictures. So basically, in a typical Android app, I draw Android apps as this kind of like vertical stacks, right? Each app is a process. It's a Linux process. Each app may have one of the activity services providers or receivers, right? So app is basically just a container for those components. So I use an activity as an example because it's the easiest. It's some kind of UI, something that you can interact with. You can press a button, right? And often you may want that button to actually do something that has to do with lower level stuff, right? So what you would do, for example, you would want to access a library, a native library, a libso. To do that, so in my world, the blue is Java and the green is native, mostly C, right? So basically, to access this piece of C code here, what we would do is we would wrap that piece of code using a JNI technology, right? And then we're going to use NDK to help us do so, right? So basically, that library would now access, for example, a device driver or something else that may not be available to you in a Java land, right? So that's essentially the motivation for this. That's what we're trying to do here. So we're going to basically learn how you can have a standard Java, or more specifically an Android component, such as an activity, a screen, talk to a native library that then may do something else in C, C++. One thing that I wanted to point out is that I find people find sometimes confusing is that who runs actually your native code, right? If you're talking about an application, right? Yes, you can bundle your native code, your SO library into your native code, but ultimately that code is still executed by Dalvik. So keep in mind that that it's Dalvik that actually runs your library, right? So, for example, your Java code that you write is going to get converted into Dalvik executable, into .dex file classes, right? So that's what's natural to Dalvik. Dalvik runs your Dalvik Java code, essentially, compiled Java code, right? But it's and so if you have some native library, that native library is loaded by the very same process, the very same VM, and it actually facilitates the communication. Right? It's a common misconception that the communication kind of happens directly, and it doesn't. It actually goes to the VM. It's the VM that's actually kind of bridging the gap between both Java land as well as the native land, right? So I just wanted to point that out. That's going to come in handy later on. So let's talk a little bit about what NDK is and what it isn't. So for one, NDK is a toolchain, right? So I've done this work before NDK existed, so having native code inside of your Android app. And basically what that meant was, because you could always do it, from very first day of Android shipping, you could access native via JNI. The problem was cross-compiling your C code on, in my case, my Mac, for, in my case, ARM CPU, right? So you need a cross-compiler, you need a linker, you need all those good things. And it just happens that those things, setting up those tools is actually pretty painful. There's a lot of work that needs to happen to you for you to get the toolchain right. NDK serves the toolchain on a silver platter. It's really easy to use. That's one of the very important benefits of NDK, right? It saves you probably a good day in just setting up the tooling. NDK also provides a way to bundle your library into your APK. Okay, that's kind of like probably the biggest benefit of it. So when I did this before NDK existed, sure, you can set up your own tooling and cross-compile your code, and you get the library, and sure, you can call that library from Java. The problem was for Java to load that library, right? I don't know how much you guys are familiar with the file system of a typical Android device, but just to kind of like really quickly refresh your memory on that. In a typical Android device, your ROM, basically your operating system, is under slash system. That is where everything happens. That's the 100 to 300 megabyte gorilla that actually contains majority of your operating system, right? Of what we call Android. So inside of that partition, there is a folder called lib, and that, along with those /vendor/lib, is actually the only place that the LD library path points to. So that's the only place that we're going to look for libraries. Okay, but the problem with this is that this is mounted read-only. This partition, right? So system is off limits to use an app developer or user, for that matter. So basically, sure, if you're a platform developer, it's easy. You just stick your library in there, you call it a day, you're done, right? But what if you're an app developer? You can't, right? So where do you put your libraries so it gets loaded? Okay. So that was the hard part before NDK. I actually did not have a good solution before NDK. Companies I worked with back then, they actually had the luxury of shipping the entire Android ROM, so we kind of repackaged it into /system/lib. With NDK, what they came up with is basically a way to package it into /data. So /data is the partition where user data is stored. So as the user downloads, starts using the phone, you download apps and play with the apps and all that. All those apps go into, well, the actual applications go into here, but the application's data goes into /data/data. So this is where every single app has its own proprietary private little sandbox in the file system, right? It's just managed by UIDs and GIDs at the Linux level, so it's pretty straightforward. But inside of these, every single application actually has a lib folder. Now they're almost always empty, but all the apps are going to have a lib folder, and so on. Right? So as you can see, they all have it, right? So basically, what we're going to do is we're going to package with the NDK, we're going to package our SO library so it ends up in this folder of our particular application. Okay, so that's the gist of the packaging part of it. Another thing that NDK does, it standardizes native platforms. So sure, you can access native, but what libraries are going to be available on that platform, right? So Samsung may have some different libraries than Motorola or than HTC, right? So NDK basically says, look, this is the small set of libraries that we guarantee are going to be there. More specifically, the headers, right? So they include things like libc, libm, libz, liblog, JNI graphics, OpenGL, JNI standard headers, and some minimal C++ support. Right? So you can always, there could be more, but this is what is guaranteed to be there from a manufacturer to manufacturer. That's what it means to be Android compatible. Right? Now, if you look at this set of libraries that they included, you may get an idea what they're trying to solve, what kind of problem they're trying to solve with NDK. Right? So they're really gearing this toward games. Right? A lot of these libraries have to do either with computational stuff or graphics, right? So it's really for the game developers the most, what this was designed for. And NDK also includes, the sample code and such. So why would you care about NDK? So now that we know what it is, why would you care about it? Well, number one reason is probably performance. Certain pieces of code run faster natively. We're gonna see that today, right? So that's a good reason. The second reason is legacy support. So sometimes you just have a library that you wrote over the years, and it's C++, and you just don't have time to recompile it or rewrite the whole thing in Java, right? So you basically just want to wrap it up in JNI and bundle it in and call it a day, right? So that's a good reason as well. Sometimes you just simply don't have access to low-level libraries. The good example of this was actually Bluetooth, right? We had Bluetooth in Android devices from day one, but we didn't have a Java API. We had it in 0.9, and then they ripped it out before 1.0 came out, the first Android release, because they didn't like the specification. Luckily, that was a good choice because it wasn't very good, right? So we had to wait until 2.0. We had to wait for years to get Bluetooth available to us in Java. But all along, we had BlueZ library in the stack, right? So a lot of people just basically bypass Java, went directly to native to get the Bluetooth stuff done. So that was a good example of using low-level libraries. Another example is cross-platform development. I was actually pretty puzzled by this one, but I kind of adopted Java super early on, thinking that it's like portable language. You write once, runs anywhere, right? That's a big promise of Java. And now what I'm seeing is a lot of companies are actually writing brand new code in C for mobile. I was like, wow, I thought Java was portable, right? The reason why they're doing that is because C, they can now recompile for iOS or different platforms like that. So certain companies are using it for cross-platform development nonetheless. One thing I wanted to point out is that using JNI, just because you prefer C versus Java, is not necessarily a good reason. It will make your application substantially more complex to debug as well. Right, so be mindful of that. JNI or NDK adds a level of complexity. So you got to have a good reason to use it to begin with. Java offers much richer API, offers memory protection, OP, productivity, all those sorts of good things. So you should, just because you only know C and you now want to program in C on Android and you heard you can, that's not necessarily a good motivation in the long run, right? It's doable, but Java usually has advantage of that. But these other motivations are usually good reasons to go with C or NDK for that. So what I'm going to do now is I'm going to kind of explain the process and give you a demo of how we're going to do this. So basically, how do you use NDK? Well, this is sort of my block diagram of how I would do it. So basically, what I would do is I would write a Java library. All right, start there. I would compile the Java library using javac, get a class file. Then I would rerun the Java library using, pass it through something called java-h-jni. Java-h is a tool that ships with JDK. And basically what it does is it looks for native methods in your code and analyzes them and figures them out and spits out a .h file, a header file, right? So you get this header file, right? Then you have to basically implement your header file. You write a little make file with pretty much a boilerplate a template, and you basically run NDK build on it. This is the tool chain, and that creates the .so file for you, right? And then basically, once you have that, you're done with the library. Now you would basically just write some kind of code that actually uses this library so we can see things working. Now this is the implementation using C, right? We can also use JNI using C++. It's slightly different. The difference is that we will still write a library, we would still compile it, but this time around we actually don't need a header file. We don't need a .h file. Instead, what we do is we use an approach via something called JNI onload. So JNI onload is a special function that gets called when Dalvik loads your library first time. Okay. And then we would basically implement that using a C++ file, and then what we would do is basically compile it using the NDK build, the same tool chain. So everything else is basically the same. So basically these are the steps that you would go through building or adding native code to your app. I'm going to walk you through both of these steps in detail. We have an example, and this example is also available on GitHub, and you can pull it down. So you can see all the steps that I'm walking through. They're basically specified here. Now, instead of just kind of going through a static page, I'm just going to open up my Eclipse and actually write this example to kind of and talk it through so you guys can actually see this in action. So I'm going to start a new project. So I'm going to build an Android app. And the app that we're going to do is an application that's going to calculate Fibonacci number, right? So the reason why I picked Fibonacci is because it's a nice little elegant, this tiny little algorithm, but it also gets really much slower really fast. So it's basically it's an exponential algorithm, right? So it gets you can see the performance performance differences between C and Java. So basically, what we are interested in is which one performs better. Okay. So I'm gonna quickly create an app. I'll call it Fib Native. Fibonacci. I'll just call it Fib. Short project. I'll say this is a Maracana Fib. I'll pick whatever. It doesn't really matter. Some stuff here. I'm creating just a hello world type of application, right? We're going to have an activity. Do I really need to pick an image? I'll skip that. You guys know how that works. And I'm going to create a blank activity. We're going to need some kind of activity just to kind of drive our code. Think of it as a test for us, for our code. I'll just call it main. So far, we got a hello world, right? Created some code. We haven't really done much at all. So, in the past, so I'm going to rewind here to the picture. In the past, I would start with a C implementation. But the tooling that Android provides for NDK as of recent is actually got much better. The R20, especially 21 release of ADT, Android Developer Tools for Eclipse, provides a lot of integration for NDK development inside of Eclipse. That wasn't the case before. So a lot of stuff before, we had to do manual steps, command line. That's why I usually lose people, right? So with that, C++ version actually becomes quite easy and simpler to implement. So I'm going to start with the C++, but then I'll rewind to C so I can kind of show you both implementations. One thing I wanted to point out I don't know if any of you are doing platform level development, actually building Android ROM and messing around with the actual not app level, but more deeper than app level. So the steps are the same, right? You're using the same technology, same everything. And when you look at it, you're going to see a lot of C++. You're going to see a lot of C++ files, more specifically, but not a lot of C++ language. Okay. Android platform. So I'm not talking about an app. I'm talking about the entire operating system. They like C++, but only a tiny subset. They use it mostly for namespacing. Okay, so you're not going to see much object-oriented C++, right? You're not going to see classes or anything like that, right? So it's a much more rudimentary sort of use of the language. So I'm going to start with this. So basically, number one is to define our library. So I'm not going to. So what I have is the activity right now. This is what boilerplate code gave us. I'll leave this for later, right? So for now, I'm just going to start with the library. So what I'm going to do is in my source, my Java code, I'm going to create a new class, just a plain old Android class, and I'll call it fiblib. So this is going to be my Java code. Let me just really quickly make the font larger so you guys don't have to makes it easier for you to read it. So, so apply that. Bam. All right, so that's a little easier. So what I'm going to do is I'm going to just define a function for Fibonacci, public long fib. And I'm going to do a Java version and a native version. Remember, we want to compare the speed. So Java version takes a long n, right? And for those of you who don't remember Fibonacci, it's basically if n is 0, then you simply return 0. If n is 1, you return 1. Otherwise, you return Fibonacci Java of n minus 1 plus fib Java of n minus 2. That's just how it's defined, right? You can look it up on Wikipedia. It's got to be true then. So that's the Java version. Now, if I want to define a native version, this is where we're now getting native with this, right? We're outsourcing stuff from Java to native land. It would look like this: public native long fib n of long n, and you just terminate it. Done. Right? So there's no body to it because we're going to implement it in C or C++. So that's basically what this would look like. So I save this file that compiles it. So basically, if you look at the picture, done with this, press save, Eclipse compiled it, I got this file, right? Now, what I would do is do something that basically showcases how Eclipse integrates with NDK. So these steps before you would have to do manually. But check this out. In Eclipse now, what you can do is you can right-click, and so Android Tools, and say Add Native Support. And simply ask you what's going to be the name of your library. And I'm going to say, fine, we're going to call it fiblib.so, right? Oh, NDK location is not set up. For some reason, it always forgets the NDK location. This is a tiny little bug when you change workspaces, and I do that all the time. So basically under Android NDK, you simply have to point to your NDK location, which for me is NDK right here. So apply, and that's now fixed. So if I do these steps again, and the native fib finish. Now what just happened is the following. It's in so you go to Properties, Android NDK, and there's only one thing to set, and that's the location. And by the way, I'm screencasting this whole talk, so you'll be able to see this video afterwards. Okay. So just so you guys know, in case you missed something. So basically, this is what happened. The Eclipse gave us some new boilerplate code, and this is it, right? So it's not much. I'm going to open it up. So we get this fib.cpp file, and all it does is it includes the JNI.h file, right? And it also gives us the make file, right? And by the way, you have these things also specified in here. So basically, this is spelling out pretty much the same thing, right? So this is the implementation in C++. So what I'm going to do now is I'm going to not worry about this file for now. I forgot to say this one. So what I'm going to do is I'm going to implement the C++ version. Now the C++ version, so like I said, they use namespace, right? And it's usually the name of your package, right? So if my package is com maracana fib, it'd be com maracana fib, and you open it up, right? So now inside of your namespace, you define your function. So we have a function called fib, or Fibonacci, right? I can just kind of come up with it. I'll call it long fib, right? Long n, right? And I would just define it. I would say same thing as in Java. If n is 0, return 0. If n is 1, return 1. Else return fib of n minus 1 plus fib of n minus 2, right? So that's basically our return. Okay, got it. So that's basically this, right? Now, one thing that I wanted to point out is in my fiblib, just a little bit about Java, there's an opportunity for improvement. Namely, these functions don't need to be dynamic. They can be static. They don't depend on any of the state of this library, right? So this would actually be better if this was a static long. And similarly, I can do it, make it static here, right? So basically, that's an alternative way to do that. So basically, and then in Java, what I could also do is make this static. I mean in C, static. Now, this is your pure C version, right? So pure C, right? There's nothing JNI-ish about that. However, what we must do now is we actually gotta wrap it in JNI, okay? So JNI has a function of, like, I'll call it fib. Let me see what would be the best way to call it. I'll call it fib n for native. So static. Now, JNI has a special data types. And I did not include this in this talk because it's a very long conversation, everything about JNI. But we have a reference document on that. And basically, let me just kind of, it's available on our site. I'll give you a link later on. But basically, in JNI, we map all the data types from Java into a C equivalent. And the reason for that is that in C, the size of an integer is not known. It depends on a platform, right? So JNI, basically what it does is it spells out the length of each type, right? So it's not arbitrary how long an int is, or long or short and so on. So basically, my long becomes a JLong in the world of JNI, right? So JLong is going to be the return type. And so I'm going to have JLong as input, right? Now, JNI also has two arguments that are always there, okay? The first one is JNI env, right? Did I spell it properly? Okay. The second argument is either a class or a file, a class or an object. So since our input is declared static, we are basically, this is basically a class property, not an object property. So the second argument is actually a pointer to the caller. So since the caller is a class, not an object, this is going to be a J class. And typically we call it class, right? That's a typical sort of naming convention for this. So that's basically my my JNI-ish C code, right? So this is now JNI wrapper. Okay, and that one is simply going to call my C code, my return fib n, right? Now, Eclipse may complain about a whole bunch of things here, and that has to do with the fact that it can't find JNI.h, and often this problem is solved by rebooting Eclipse. I'm serious. So let's see if I'm right. But this is one of the bugs that I've seen before. And basically, certain environmental variables are missing when you add native support. The behavior is different from Windows to Mac on this one. But as you can see, the problem is just gone. Right? No more problem. That was the easiest fix. So basically, it can't find this JNI.h, and that is where you have all the JNI related stuff. So it's super important. So, cool. So I have my header. I have my pure C function. What we need to do next is we basically need to provide a table that's going to map an external type from Java to an internal C or JNI representation of this, right? And this table looks like this. I'm going to actually, as opposed to typing it, I'm just going to copy it and adjust it, because this is sort of what you often do. You don't normally write this from scratch. So let me fix this, and let me fix this, right? And let me explain what this is. So basically, this table maps what is going to be known in Java to what we have in C. So this is a pointer to that guy, right? And this is how it's going to be known in Java. Now, this thing here is a funky signature of this function. So this here means that our Fibonacci n in Java takes as input a long and returns as output a long. Okay? So this becomes, so basically, because we defined it in C as long, fib n long, okay? The long translates, and you wouldn't know how it translates until you saw the table, but there's a table that we have some. This is, I believe it's a JNI convention. It's actually a JNI documentation. This is actually, this JNI reference doesn't even come from our Android course. It comes from our Java course, because it's the same. But basically, these are the mappings. Where, you know, a Boolean is Z, byte is B, but there are a couple of ones that don't make sense, like a J for long, and so on. And then some become really funky, right? Like if you have strings, or if you have a string array, then you get this business of like L, Java /lang/strings semicolon. It just becomes like this crazy sort of encoding of the signature of a function. You might have seen it before, and there's actually a way to have this automatically figured out using Java P. So if you do Java P on your code, you can actually have it print out the proper signature using this convention. But it doesn't make a lot of sense. This is where you sort of go to a table and try to map it to a table, and that's you got to use a reference document to figure out what is what. But basically, in my code, in our C++ code, this means this is basically the Java signature. Input is n is long, output is long, the name of the function or method is fiban, right? And this is the pointer to this. Now, we're almost done with this. There's one more thing to do, and that thing is to basically create the, so let me just kind of show you the table where we're at. So we are here, right? So what we now need to do is we basically need this JNI onload function. This JNI onload function it gets called first time the library is loaded, and it's almost always exactly the same. There are like 2 lines of code you change. So as such, you usually copy paste it. So I'm just going to do that because it doesn't change from a project to a project. So so basically, what I have in here is JNI onload. Okay, so I'm gonna just copy paste it from the course material, and I'm gonna put it in here. So let me explain what this guy does. And there's one thing that I forgot. I need to say that I'm using namespace com Maracana fib, right? So if I'm using that namespace, and then I need to specify the path. So basically, here what I'm doing is I'm saying for this Java library, so in our case it's going to be, this is just fib, use this method table, and the method table is this, to basically reference stuff. So we are registering, at the load time, we're registering a table of mapping from the world of Java to the world of C. That table is really here. This is the table. It would grow, right? For each function that you want to map, you would have a line item in here. And it's mapping a Java type to a native type. but we need to register at some point, and we're doing that registration during JNI onload, which is a sort of a, it's a system callback. It gets called initially when everything is loaded up. So my code is pretty much done in this case. What I can do now is, as a matter of fact, well, you can't actually see it yet. So my code is pretty much done. I just want to explain the make file. Android uses a make system, as you guys may or may not know, right? This is true for the platform as well. And so this make file in NDK is no different than gazillion make files that you find in Android open source, right? Of the entire platform. Basically, every single make file in Android starts with the very same 2 lines. Why? Well, because they don't use a recursive make, they use a make that basically builds a gigantic make file, right? So they do a lot of include. And the reason why they do that is because, as such, the make system lends itself nicely to parallel compilation. Because it takes hours to build Android anyway, so this kind of helps with, map reducing the project, right? The build. So that's why you have the first 2 lines. The last line basically says what do you want to produce as the output. And it's always going to be there. The only difference is you may have a different something here. So build shared library produces an SO file. Build executable produces a bin file. Build package produces an app. Etc., etc. There are a handful of these kind of targets. And then this is simply saying compile this and stick it into that. This is the name of the module, and whatever you put in here is going to be a lib that.so. Okay, so that's basically what the make file is. So I'm just really quickly now gonna, so basically at this point, oops, I did not want to insert this tab. At this point, what we have is we have done all of this, right? Almost. There are a couple of things that are left for later. Now I'm going to just whip together this really quickly so that we can actually see this in action. So I'm going to just build the world's simplest UI by basically deleting this here. We need a place to put a number, right? So number, bam, I'm going to put the number here. I'm going to change its ID to input. I'm going to put the button so we can click it and so something happens. ID is going to be go. And I'm going to add a text field for the output. We're just going to dump the output in a text right here, and I'm going to make that be large and take the rest of the screen. And I'll call this output. Bam, done. So that's going to be our UI to test these things. And only one minor thing that I'm going to go do is I'm going to wire the button. So what I'm going to do for the button is I'm going to say Android on click. So basically when you click it, it calls on click. So now our Java code is going to be super simple as well, the activity, right? So I have edit text input, text view output, okay, organize imports, and automate this, and basically public void on click gets called with view v when the button is clicked. So let me just kind of really quickly find these guys. So input is going to be edit text, right? And find view by ID, r.id dot input. That's it, right? And output is going to be text view. Find view by ID, r.id dot output. Fine. So organize imports. Everything's good. So what I need to do is I need to get my input. So long n is going to be long dot parse long from input dot get text to string. All right. So just really quickly to get a 10. User typed in some number, all right? So now we're ready to actually drive this code, right? So basically what I can do is now let's do a Java version first. Java, right? So in Java, what I'm going to do, just to test things are working, so result in Java is, so long result in Java is going to be fiblib.fibj of len, right? And I'm going to print it out. So I'll say output.append, I'll say string.format, and I'm going to put something like \n fibj %d is going to be %d, and we're going to put n comma result j, right? So just kind of putting some output out there, and I'm going to do the same for long result n is going to, well, actually I'll comment this out first, fiblib.fibn of n. Okay, so I'm going to comment this out for now. Okay, let's run this and see if it works. First one. So this is going to crash. Well, it's going to work for Java, but it's going to crash for C. So if I put some number 23, bam, there's my calculation of Fibonacci for 23, right? 26, bam, there's a number, right? So far so good. Now, if I enable my Java, my native stuff, because that's exactly what we wanted in the first place, right? So I'm just going to recompile this, rerun it, to see what happens. So 23, go, bam, crashes. Why did it crash? Anybody? Can't find the library, right? So although I have a library, I never loaded it. So you're going to see this notorious exception when you do anything like this, unsatisfied link error. Basically, Dalvik can't find the library. Not library, it can't find leben. As a matter of fact, it calls leben right here, but then it doesn't resolve it. It's looking now its function table and can't find it, right? So what I'm missing here is actually loading the library. Now, we typically do this as a static, which means that it only happens once ever when Java library is, so when Java code is loaded, it then does this. And what we do here is we say system.load library and then the name of the library. Okay? So now the name of the library that we want is going to be not the name of the file, not libfib.so, another common misconception, but it's going to be the name of the module, which is a fib. Yes, the file is going to be libfib.so, but we're loading a module, not a file. So keep that in mind. So if I just say fib here, okay. By the way, I don't know if you noticed, but there's now a new file here under libs that has libfib.so. Right? That's our SO file. That's what we created. So if I run this, now let's see what we got. 23, go. It crashed again. So this time around, I don't know why it crashed. Let's take a look. Still couldn't find the library. Aha! Any idea why it crashed now? I'll give you a hint. I'm running an x86 version of the emulator. So the library that I compiled, or the default library that gets compiled, is actually ARM5, right? So that's what is in here. So there's another file that you can throw into your JNI place. JNI is where you keep all your native work, right? That file is super simple. It's basically a one-line file. Let me see where we have this template. It's a one-line file that specifies the, let's see, something like this. So it's called application.mk. So what I'm going to do is I'm going to create a new file here, just a plain old file. You got to spell it properly. Application.mk, capital A. Okay. And this is the file where you can drive the behavior of the toolchain. So you could, for example, say, I want to build for x86, ARM, and ARM7, for example. Or you can just say all, and it's going to compile for all known toolchains that you have in your NDK. You may have only one, but you may have like 4, for example. So if I run now, notice what's going to happen in my lib folder. I actually have now the same library compiled for MIPS, x86, ARM5, and ARM7. Different architecture, right? So I applied 3 different toolchains, which is pretty amazing. So that's a pretty cool little benefit, right? So if I rerun this, 23. Go. All right, there we go. I got the number both in native and in Java. Now, you guys never cared about the actual how the number, right? Of course, they're going to be the same because they're the same algorithm, right? We cared about the performance. So let me just really quickly time this. So I'm going to say long time is going to be system.current time milliseconds. Time is going to be system.current time millis minus time. And I'm going to print it out here, %dms, comma time. I'm going to do the same thing here. Time, and do this in reverse, %dms. All right, and let me surround this with a little timer. So this is native, right? And all right, so let's now run this again and see what kind of time difference we got. So 23, damn, this is pretty fast actually. Right. 23, let me try 27. Now keep in mind I'm running a uber accelerated version of x86 device. So it's pretty fast to begin with. 33. Okay. So as you keep getting, that's what I like about this algorithm. The numbers become increasingly slower as you add a little bit. So as you keep running this, you start seeing some patterns, right? So these are the patterns, right? So you start seeing about an order of magnitude difference between C and Java in this particular algorithm. Okay. But this has to do with the fact that it's a recursive. If I actually did, I don't have time to do this, but if I, because everything recursive can be done iteratively. If you did this iteratively, the numbers, you would have to time it in nanoseconds because the difference is, they're way faster, right? But the numbers become much smaller, less of a difference, right? So it doesn't mean that Java is always 10x, 20x, 50x slower. Right? It's just that in certain algorithms, one may work better than the others. Yeah, you had a question? Oh yeah, it's going to be different. Yeah, it's going to be different. And a better way to, if you guys, I don't know if you're familiar with the DDMS, but if I attach DDMS to this and I start tracing, profiling my app, and I run the same thing, I'm going to go with a much smaller number because this is going to run slow to begin with. And the reason why it now runs extra slow is because I'm actually doing analysis on it as we keep on going. So Dalvik is actually collecting a ton of data to begin with. So that's not, it's a small number, 27, that flew before, right? But now because of the tracing, it's actually uber slow. And now it's done. I'm actually gonna, let's see what we get as the trace file on this one, but it's gonna be quite interesting to see the difference between the two algorithms once it pops up. Eventually, I guess it takes some time to analyze this. All right, so here's the trace information. So basically, and every once in a while, I don't know why, as of recently, the graphics disappear. So you can't really see visually what I'm talking about here. That's a bug. But there's my call. I guess if you click on it, it kind of hints where it is. But basically, between those 2 points where I did my execution, fibj took basically 90% of the time, right? So C was like less than 10% of the time. And for that number, whatever the number was, I forget, it executed, we basically had, what's the number of calls? We had one call plus 269,000 recursive subcalls, right? So that's kind of like why, Java is naturally not good with stacks. It's better with registers. It's the opposite for ARM. So that may have to do with that. But that's a little bit about, the performance differences. So you remember, performance is one of the good motivations why you would care about NDK. Just really quickly to give you guys a sense, if I was going to do this in C++, it's not that different. But it's a little bit manual. So what I would have to do is I would have to go to AnDevCon Fibonacci, yeah, that's our project. So this is our project. So I'll have to run java h-jni to get that header file. And because it doesn't know my class path on the here, I need to specify my class path, which is going to be in classes because that's where Eclipse keeps your classes that are compiled. And I would redirect the output to JNI folder because that's where we keep all the output. So the file that I want to process is com.arakan, not file, but a class, fiblib, fib.fiblib, right? So what this does, if I didn't mistype it, is this tool basically goes and opens up this Java file. And it basically reads through it, looking for only the keyword native. When it sees keyword native, it actually creates a signature for you. So let me refresh my Java H here. Refresh. And notice that now there's a new file, which is the header file for C. Okay? So this is the file that Java H created for you. Now, in this file, what you really care about is just this signature. So if you were doing this in C, you would copy, paste the signature. You would create another file called, let's call it fib.c. So it's going to be my C file. Okay, this is where I'm going to implement this. I'm going to pound include the com maracana fiblib.h. I forgot my quotes. Okay. And then what I would do is I would basically implement this algorithm here. Since we already had that implementation, I'm just going to copy paste it. So remember our algorithm was in pure C, just this, pretty straightforward. So then the C version would simply call that file. Let me reformat this and return fib of n, right? Reformat. Now, it doesn't know about your parameter names, so you have to kind of give them a name. So env, this is typically class, and this is our n. Okay? So that's my C version. Now, I just need to change in the make file, not to use CVP, but to use C version. It's actually a lower path, right? And if I rerun this, now we have the same thing, but this time around, it's in using the C implementation versus the C++ implementation. There's a difference between the two. The difference is slight. In C version, keep in mind, so the main kind of magic behind this is JNI. That's the hard part, right? I'm just talking about NDK, which is sort of the wrapping, the packaging. It's an anti-development kit. It's a kit around JNI. If you want to learn this really well, you got to understand JNI. So JNI is a naming convention. So basically, how does your Dalvik Java find your Dalvik C, right? That's what is going on. So with C version, it's looking, when you say I want to call fibn, it looks for Java underscore your package underscore your class underscore your method. It's a naming convention. So it finds it every single time via this naming convention, right? So every single time there's a lookup based on a convention, okay? So you're paying a price, tiny price, but price nonetheless, every single call, okay? Now with the C++ version, it's slightly different. There is no lookup every single time because it's a pointer. We define a pointer table. But we pay the price up front because we had to register that table via JNI onload. So we are paying a smaller penalty, we are paying a penalty up front, but getting to reap a benefit every single subsequent call, sort of, right? So Android platform tends to use C++, this very approach. Like you could copy paste this JNI onload. That's what is in Android everywhere, right? So they tend to use this quite a bit as the approach to basically load the classes. And so, and this code is executed when you do this guy, when you do this call here. But it only happens once. That's what causes JNI onload to happen. Okay. So that's basically this example, the Fibonacci example. I just kind of want to wrap it up with, doing stuff in JNI can be a performance boost for your app, it's not always the case. And it's kind of like if a project is really, really small, you're going to pay the penalty of not only more complex development time, so not only is your carbon cycles, but also in terms of the silicon cycles, computer cycles, you're going to pay the penalty in terms of the bridge, the JNI bridge, this lookup, right? So it's kind of like outsourcing, right? If you have a tiny little project, right? Like if I have a bigger project, it makes sense to outsource to India, China, some place where they're more efficient in getting stuff done, right? But if I have a tiny project, like writing an email, the overhead of outsourcing that project, is big enough that it doesn't make up for the difference in efficiency where you outsource it to. So don't outsource small projects to see big projects make sense. Like for example, drawing big graphics, or like I keep using Angry Birds as an example. Angry Birds uses this kind of there's libangrybirds.so, right? I don't know if you ever looked inside, but there is, and they use it for their physics engine for calculating the trajectory of the bird and other kind of computational stuff like that. So in that sense, in that case, NDK and JNI make sense. So that's basically the gist of this that we covered. All the source code is in here, and that's the summary. I posted this article online, and I'm going to provide a video of this article as well, of this talk later on, just so you guys know. And just one thing that I wanted to mention: make sure if you're looking at this, also look at the post on JNI the JNI reference, for which I'll give you the shortener, which looks like this, right? So that's also super useful, so you know how JNI works. Yeah, you had a question? The question is, can you have C call back into the view itself? So the C has access back to Java via that either JClass or JObject. So basically, you would then, again, yes, you can call from C back to Java, but it would need to go through the wrapper, right? So it would need to, you would provide how that happens. Actually, in this article, we talk about that. There are examples of how C calls Java. It works through introspection. So basically, C now needs to find a class. Then in the class needs to find a method, and so on and so on. One thing to watch out for is when you're updating the UI is that you got to do it on the UI thread. But in this case, everything is actually running on a UI thread. Although it's C, I'm running it from my thread, from the main thread. So there's no thread issues whatsoever, right? But keep that in mind in general. It's not so much is C updating Java UI or Android UI, it's more of a which thread is updating the UI thread. So yeah. Cool, well thank you guys. I'll make the video available afterwards, so the slides are available already.